Okay, it's 4:05, so we're gonna get started now. Thank you for coming to day 2 of lecture. I'll start with some like course announcements. So as a reminder, this is our website. You can access like all the details about our class from there. Second, we now have a Piazza. You all should have gotten an email about that earlier today. And finally, we uploaded yesterday's recording to our class website where you'll be able to find all of our past recordings there as well. So today we're going to be covering day 1 of our range query lectures. So today we're going to be going over prefix sum arrays. So in general, range query problems are in similar style to this. So basically, you're given an array of integers and a bunch of like queries or like questions. And each query consists of kind of like a range. So like a left endpoint and a right endpoint. And you want to output basically the sum of all elements in that range. So one kind of so some example is given this array up top, you could like you would output like 2 plus 4 plus 5, which is 11. Could query like 5 through 6, which is like 1 plus 1 is 2. You could query the entire array by starting at like the first index and ending at the last index, which would give you 24. And you can also just query a single element, like from 3 to 3. That would just output the single element. So how can we solve just by brute forcing it? So what this involves is just for each query, you want to find the sum of elements from L to R. So you can just iterate through your array from L to R, summing up individual elements as you go. So this is a sample implementation of how you could do that. This algorithm works since it's just simulating the problem statement, but it's a little slow since the time complexity is O of NQ. For each of the Q queries, you have to iterate through up to the entire array, which contributes O of N for every single query, making the total time complexity O of NQ. And with constraints as big as like N is like 2 times 10 to the 5, Q is 2 times 10 to the 5, this won't run in time. So how can we speed this up? We'll first go through some basic notation. Um, so when we denote ranges, we'll use like the normal like open closed bracket notation, where like a square bracket means a closed like inclusive interval, and an open bracket is exclusive. So for example, 2 through 5 would mean 2, 3, 4, 5. 3 through 7, like open bracket, would mean exclusive, so only 4, 5, 6. And then um square bracket 1 and then round bracket 6 means that we include 1 but exclude 6. So like 1, 2, 3, 4, and 5. So we'll be starting from here, we're going to be zero indexing all of our arrays. So the first element in our array will be 0 instead of 1. So as a recap, our problem, you're given an array and you want to find basically the sum of a bunch of ranges that you're asked about. So one thing we can do is instead of just jumping straight into answering all these queries, we can first construct what's called a prefix sum array. And this array just has the the sum of all the elements in the original array that have index equal to or before it. So for example, this first element in our prefix sum array will have 3 because the sum of 3 is 3. Then the next one, 3 plus 6 is 9, so we put a 9 there. Next one, 3 plus 6 plus 2 is 11, so we put 11 there. And in general, just every element in our prefix sum array contains earlier. So assuming we construct this array, like what can we do with it? So when we get a query, it's in the form like what's the sum of elements from like 2 to 6, for example. So what that would look like is in our original array, this is index 2, and this is index 6, and we want to sum up 2 plus 1 plus 8 plus 3 plus 5. How can we do this with our prefix sum array? Well, why don't we start by getting this element? This element includes everything before it. So that's 3 plus 6 plus 2 all the way to plus 5. We've added a bit too much here since we only want this gray interval, whereas we have like an extra 3 and 6 beforehand. So how can we remove that 3 and 6 at the beginning? We can simply just subtract that 9. While this 28 gives us our entire array, ending at the 5, the 9, and kind of like as a concrete like equation intuition, the red one is the sum of everything up to index 6, the blue one is everything up to index 1, and these two terms cancel it. So we're left just with our gray rectangle. And to like do a concrete calculation, the sum of everything inside is the gray rectangle is 2 plus 1, which is 3, plus 8 is 11, plus 3 is 14, plus 5 is 19. And similarly, if we just subtract 28 minus 9, that also gives us our same sum of 19. So using our prefix sum array, instead of iterating through our entire range, which can take up to O of n time and is pretty expensive, we can just subtract two numbers and get the same answer. So that's kind of like an intuition of why prefix sum arrays are a lot faster than our brute force implementation of going through each element and adding them one by one. And the way we can do this in code is with this formula. So to get the range of L to R, in this case 2 to 6, we can take prefix of R, which is the sixth element, and then we want to subtract off L minus 1, since that's the sum of everything less than L. So with this formula, you can calculate the sum of any range in just a single subtraction operation. One slight problem with this is that, or like inconvenience, is that if we want to do the sum of something like from 0 to 4, our formula would tell us to do like prefix of 4 minus prefix of -1, which is not good since that would introduce an index error. So there's several ways to approach this, one of which is just to check like, oh, if the index is 0, just like return prefix R instead of a subtraction. But there's also a more cleaner and I argue easier way to do this. We can do this by re-indexing. So again, when we query 0 through 4, when we apply our formula, we'll have to subtract something that's not in our prefix sum array, which will introduce an index out of bounds error. And we can index the array differently by just shifting everything over to the right by 1. So we introduced the 0 at the beginning, and we took our entire array and shifted it to the right. Index 3, the 12, is now index 4. Like we shift everything over to the right by 1. And since everything is shifted to the right by 1, instead of querying prefix of R minus prefix of L minus 1, we can just add 1 to those indices to query instead prefix of R plus 1 minus prefix of L, because we shifted everything over 1 to the right. This also helps us in that we now no longer have negative indices, so this can apply even when we query a left endpoint of 0. Does this all make sense? Like, are there any questions about, I guess, what we covered so far? Prefix sums, reindexing. All right. So if we have a prefix sum, we know how to answer queries with them, but we still first need to build up our prefix sum array. So with our re-index definition, we have that prefix of I is the sum from like 0 all the way to the element before it. So for example, this 11 would be 3 plus 6 plus 2. And how we can do this is kind of intuitively by doing something like this, where notice that this 12 is 3 plus 6 plus 2 plus 1, and this 20 wants to represent 3 plus 6 plus 2 plus 1 plus 8. So instead of recomputing all of this, we already know 12 includes these four numbers, so let's just add 8 and 12 to get the entire sum. So we can construct our prefix sum this way by just doing prefix of I plus 1 is the previous prefix sum plus the current element. So this allows us to build our prefix sum efficiently in O of n time, since we're just iterating through the array, adding the previous prefix and the current element each time. And as kind of like for the time complexity of this, the construction takes O of n time. Each query, since we're just doing one subtraction operation, each query takes O of 1 time. So the total time complexity is like O of n for the construction and then O of q for the number of queries for a total time complexity of O of n plus q, which is a lot better than our brute force implementation of O of n times q. So now we'll go over a coding demo of, I guess, like implementing this live. So this problem is just the same exact problem we just went through. Like give an array, answer q queries about the sum of the values in that range. And so here n and q are like pretty big, so we can't use our brute force. So I'll open up our coding thing. Our first two things that we input are like the length of our array and the number of queries. So I'll just go ahead and do our like input thing that we covered last time. And then so what this does is it gets our first line of input, splits it into integer n and integer q. Then we'll get our array. We'll call it R, and then it has to be a list of ints from the next line.
Boss, can you zoom in?
Oh yes, sorry about that.
Okay.
This is better?
Yeah.
All right.
Actually, low.
Oh, oh, wait. Okay, I guess we can work with this. Okay. So after this, we have a bunch of queries that we need to answer. So let's first try the brute force implementation and see how it does. So we have queue of these queries we need to answer. So we'll iterate through each of them. Each of them consists of L and R. And notice that in our problem, our indices are one index. They go from 1 through n instead of 0 to n minus 1. But in code, we always work with 0 indexed. So we'll subtract 1 to each of them to make them 0 index. Now we can simply, our answer is just the sum from L all the way to R inclusive. So this list slicing, the second term is exclusive, so we'll add 1 so that it covers R as well. And then we'll print answer. So we have that our program outputted that the sum from indexes 1 index 2 through 4. So that's 2 through 4 is 2 plus 4 plus 5, which is 11. It said 5 through 6 was 2. It says the entire array is 24, which you guys can double check. And index 3, the sum is 4. And they also provide sample outputs here, which we can compare. So it's the same. So let's try and submit our code, our brute force code to the judge and see what it says. So it got time limit exceeded. So what this means is that it was too slow. So like the bound of 2 times 10 to the 5, our NQ solution took too much time and we need a more efficient solution. So let's try speeding this up with prefix sums. Before we answer any queries, we need to construct our prefix sum array. So we'll call it pref, and it has size m plus 1 because of our reindexing approach. So there's a 0 at the beginning and then like our normal prefix sum array. And we initialize everything to zeros at the beginning. So we can use our construction equation here where the prefix of I plus 1 is the previous prefix plus the current element. Answer to construct our prefix sum array here. So we'll iterate through our array and we'll do prefix of I plus 1 is prefix of I plus array of I. So now this should construct our prefix array in just O of n times, since we're just doing one for loop through. And to do like a sanity check, I'll print out our prefix sum array. And we can see, yeah, so the first element is 0, 3, 5, 9, 14, and so on. So our prefix sum array looks correct. So we can now try to answer queries using it. So instead of using our sum, which is expensive and takes O of n time, since we iterate through the entire array here, we instead use our formula that we defined back here, which is the sum is prefix. So this basically like gets our right endpoint and then subtracts out everything that we don't need before our left endpoint. So let's try this again and see if it gives us the same answer. Yeah, so this looks the same as our intended output. So this should be much faster since this loop just takes n time steps to run, and this loop takes O of q time steps to run, which should pass. Yeah, so instead of getting time limit exceeded, we got accepted this time, and our code took 210 milliseconds to run, which is a lot, pretty fast since the time limit here is 1000 milliseconds. So that's kind of like how you can speed up this kind of range query problem using prefix sums. Um, Here's another implementation that you all can reference once we put out the slides after this. You can also access the live coding we did. The link will still be here and you can view the code we typed. So what are some of like advantages? Like it seems pretty good, right? So there's some clear advantages. The queries are O of 1, which means that they're constant time. Every time you do a query, it's just one subtraction operation. So they're really fast. They're also really short implementation. In our coding took like 2 lines and the query took 1 line. So it's pretty fast to code and very clean to write. But there are some downsides to this too, in that it doesn't support updates. So like once you have your array, you can't make everything in your prefix summary. So the array has to be static in this case. And it also doesn't support every operation you can think of. It supports some because it has an inverse. Like when you query a section of the array, you need to query like a prefix and then the inverse, which is subtraction of like the stuff you don't want. But it doesn't work for things like min or max because they don't have inverses. Um, Tomorrow we'll be covering a data structure that does allow both of these to happen, complicated to implement. But for now, prefix sums perform very well when we don't care about this bad stuff. So here's an example of a problem that can be solved with prefix sums. I'll briefly explain it and give everyone some time to think. So you're given an array of booleans, which means that everything is either a 1 or a 0. And you're given a bunch of queries again, but instead of doing the sum, you want to compute the bitwise OR, which means um, this is like the truth table of bitwise OR. As long as something in your range is a 1, then your bitwise OR expression will return a 1. And if everything is a 0, it will return a 0. Understand what bitwise OR does, like what the queries are. If anyone has any questions, feel free to ask. Okay, I'll give everyone maybe like a minute or two to think about this, and I'll ask for ideas afterwards. Feel free to talk. Okay, does it possible? Yeah.
Score. And you know, like if you have one true, then the whole thing is true. And you only need to like figure out where the last false is, or like the first true is, or something like that. So like go through them as soon as you see a true, you know that everything after that will validate true because it's one. And then move forward with all.
Wait, our queries are like they can like come in random places.
So they can come in random places.
Like they can be in the middle, like any L and R.
Oh,
Yeah. Um,
But you do a prefix array, and then when we query, if they're like, so if the sum value is greater than zero, then it's gonna validate true. If it's equal to zero, it's gonna validate false.
yeah, that's right. So, um, we can, oh, I guess first here's an example test case. So if we query from 0 to 3, like will be 0 or 1 or 0 or 1, which will output 1 since there are ones in there. But if we query 6 or 7, then it will be the last two, and the answer would be 0 because there's no ones in that section. Yeah, so the basic solution idea, like you said, was that the answer will be 0 only if there's no ones in that range. So what we can do is we can just do a prefix sum or like construct a prefix sum array like normal. And then every time we do a query, we look at the prefix sum in that range. And if it's 0, that means they're all 0. Since they're all 0 or 1, the prefix sum there, if the interval sum is 0, that means everything in there is 0 and our OR evaluates to 0. But if our prefix sum query evaluates to something that's non-zero, that means there must be at least one in that. There must at least be a one in that like range. So our output will be a one. So this is kind of like a pretty cool application of how we can use range queries and prefix sums to not just solve like the standard template prefix sum problem. And you'll be able to do a lot more practice after class when we release our problem set. So far, we've been covering prefix sums on one-dimensional arrays only. But there's nothing stopping us from going up to 2 dimensions or even higher. So the classic prefix sum, instead of having each element in our prefix sum array correspond to the sum of everything before it, it corresponds to the sum of everything like to the left and up of it. So for example, this 36 corresponds to the sum of everything in that gray rectangle. Similarly, this 51 corresponds to everything there. This 21 corresponds to the 2 by 2 square there. And yeah, so how can we do queries with this kind of thing where everything in our prefix sum is like the top left rectangle ending in it? So if we wanted to query this gray rectangle in the middle there, um, it's not as clear as with one-dimensional prefix sums, how we can just like take something and subtract dimensions, right? But we can start in a similar way. If we take this 44 here, this is the sum of everything in the 3 by 3, like here, which includes our gray rectangle. But we have some extra things, like the 4, 9, 12, and like the 2, 5 up there. We want to get rid of them since we don't want to include them in our sum. So let's try and just subtract out these two things, where this 25 consists of like the 9, the 12, and the 4, and this 11 consists of like the 4 plus 2 plus 5. So if we subtract off these two blue circles, we'll remove everything that's outside of this gray rectangle. But there's one slight problem with this. Since if we look at the 4 in the top right corner, when we add the 44, like it's included once. But when we subtract the 2 blue circles, we're subtracting it twice since it's included in both of them. So how can we fix this? We can just add it back in. So in this example, the gray rectangle sums to 3 plus 2 plus 6 plus 1, which is 12. And similarly, if you just perform the 44, subtract out the 2 like sides that we don't want, and then add back in the corner that we double counted, we get the same result. And this is also O of 1 operation, since for any like rectangle we query, we only need to do like we take something, we subtract 2 numbers from it, and then we add another number. And this is a constant time operation since we're doing a constant number of like addition and subtractions. So some more intuition for kind of why this works is we take our like really big rectangle, we like subtract all the stuff we don't need, but then we like double counted this, so we like add that back, and that gives us our rectangle that we desire in our query. Are there any questions on, I guess, like how kind of like why we add this back or anything about 2D prefix sum queries? Yeah.
I guess, how do you always determine which elements to subtract?
Oh, yeah. So in this case,
For example, how you,
like for example, if it was like a 3 by 2 rectangle,
yeah,
so we'd first start by like querying the bottom right one.
Yeah.
So that includes like everything. And then notice that we still have, oops, sorry. We still have like this kind of row 28 to get rid of here. And we also have this extra row, so we'll subtract off the 11. But then this is also double counted. And kind of as a geometrical like way of explaining it, if you take your like gray rectangle, your red circle will always be at like the bottom right corner. Your blue circles will be like kind of like one like out of them, and then the green circle will be like to the left and up of the top left corner. I guess yeah, that's pretty much how querying for 2D prefix sums work. But we still haven't gone over. Oh, I guess first, the same issue happens when, for example, here we want to query something that starts like in the top left corner. We'll have to like this blue circle will move out of the grid, this green circle will move out of the grid, and this blue circle will also. So we'll have out of bounds errors unless we do reindexing again, where we kind of like shift everything to the down and to the right. Instead of going out of bounds, we'll just have a 0 there. Now to construct a prefix sum, there's this long equation up there, but I'll go through it step by step. So let's say we want to calculate the prefix sum of like everything in this 3 by 3 rectangle. First, we'll like have this element in there, since that'll definitely be in the prefix sum. Then we can look at the prefix sum to the top of it. So now after we add this in, we've included like kind of these 7 squares. Then these 2 squares are still missing, so why don't we query this one as well? So like add in these 2. So if we do that, we have this kind of configuration. So every square has been accounted for, but this rectangle has been this square has been accounted for twice. So then, similar to how we treat this with queries, we'll just subtract off that square again. And after we do this, everything has been counted up exactly once. And this is also a pretty fast operation with just 2 additions and 1 subtraction. Yeah, so as kind of like a demo for how we could construct one, we'll go row by row, going from like right to left. Since if you look, you only need prefix sums that go like here, here, and here. So if you go row by row, um from left to right, you'll be able to have everything you need already computed. How we do this? Where I'll go to a more interesting case. So for example, to compute the sum of that 2 by 3 rectangle there, you would take 2, which is like the element in the square, then you'd add like the 2 adjacent ones, and then you subtract off the thing you double counted, which will give us a sum of 28 for that 2 by 3 square. And we will keep building this up until we filled up our entire prefix sum array. This construction again takes O of however big your array is, your grid is, since you're just doing a single construction, you're doing a single operation or like a constant number of operations every single time you iterate through. And similarly, the queries again are O of 1, so this is a pretty fast algorithm. We'll now go through another example problem for prefix sums, and I'll give everyone a minute to read this. Can you see okay back? Okay, so this problem is basically just 2D prefix sums where like a dot is like a 0 and a star is like a 1, where we want to like count the number of like trees in a square. And we can do that just by like summing up the number of ones there. And so I'll now solve this in Python. One thing to note is that they give you the queries in kind of a weird format, um, like y first. That's because usually when you index things, the row comes first, then the column. So like y comes first, then x. A little bit confusing, but we'll get. So we'll start with our like input template. We start with n and q, and then we'll have to read in our grid. So our grid comes in this weird format where it's like a bunch of stars and dots. Um, so we want it to be an array so we can like um or we just want yeah, we want it to be an array so we can access things easier. Generally it's a good idea to convert things into arrays or lists before doing things on them, especially if you need to update them later. So we'll do list of input dot strip. What strip does is it removes any like surrounding white space, like new lines from the ends of lines. So we'll just be left with our grid. And then we'll do this for every single row. So let's try like printing on our grid just to make sure it's fine. So, so this will print out our grid. Yeah, so our grid is now converted into like a list form, like star, dot star, dot dot, star dot star star, so on. So now we have to construct kind of like our prefix sums. So going back here, um, here where we like take the current element, we add like the adjacent prefixes, and then delete everything that we've double counted, we can construct our prefix sum here as well, like that. So we'll iterate through the same way, rows like from top down, then left to right. Then we first need to get the value of what's at our grid. Since right now it's like dots and stars. So I'll say value will be equal to like 1 if grid, oh, ij is equal to a star, and otherwise it'll be a 0. Then we do this formula where a prefix of I plus 1, j plus 1 is equal to like our current value. Oh wait, I'll first finish this. Plus prefix of ij plus 1 plus prefix of I plus 1j minus prefix of ij. Something I forgot to do is to first initialize our prefix sum array. So this will be a n plus 1 by n plus 1 two-dimensional array, and we'll initialize them all to zeros. It's n plus 1 times n plus 1 because of our reindexing. So there's like padding of zeros. Okay, so now that we've made our prefix sum array, let's print it out to just see what it's like. And this just prints them out in like a nicer format. Yeah, so we have our like padding of zeros up here and on the sides. Then like let's look at this 3 right here. So starting from here and like this 2 by 3 rectangle here, so we have 3 trees, and if we look, we do 1, 2, 3. So it looks like our prefix sum array, our 2D prefix sum array is working as intended. So now we can go through our queries and try and answer them. So we have a queue of them. Each of them is given in the format y1, x1, y2, x2. And again, these are 1 index, so we want to convert them to 0 index. Now we have like the indices we want. We want to query from y1, x1 all the way to y2, x2. So using our query formula, we get that the answer is prefix of y2 plus 1, x2 plus 1. So this gets in our reindexed prefix array, basically like everything that's to the left and up of our bottom right corner. But now we have to subtract the things that we don't want, which is to the left and to the right of like our left and top edges. We want to subtract off everything to the left of our left edge and everything above our top edge. So we'll subtract prefix x1. We'll also subtract off prefix of y1, x2 plus 1. So this subtracts off kind of like our 2 edges. And then finally, finally we've subtracted off that like corner twice. So we'll add it back in with prefix of y1, x1. So now this basically simulates kind of this thing in code, or sorry, it simulates this in code where we take like y2, this is like y2, this is like y1, y2, x2, this is like y1, x1. We'll take like y2, x2's corner, subtract off like y2, x1, subtract off like y1, x2, and then add back in y1, x1. So after we get our answer, we'll just print it out and we'll see what our code outputs. So we say, let's first check. Okay, so our sample output is correct. There should be 312. We got 312. You can also check it by hand. So we say from 2, 2 to 3, 4, So from here to here, we said there should be 3, which is correct. Then we can check from 3, 1 to 3, 1. So 3, 1 is this one. And like from that one to that one, well, it's a tree. So that's that single one contains one tree, which is what we have right here. And finally, from 1, 1 to 2, 2 is this 2 by 2 rectangle up here. That's these 4. And this has 2 trees as well, which we found correctly. So now let's submit our code just to double check. Yeah, okay, so our code works. It ran in 340 milliseconds, which is well under the time limit. If we didn't use prefix sums, we would have definitely went over the time limit. And yeah, so that's one problem where you can use like 2D prefix sums to greatly speed up your program. So I guess first, are there any questions about the code here? Any concerns? Yeah,
But in the line where you did the answer equals the prefix.
yeah,
So the plus ones, you're adding back the ones because of the padding.
yeah. So I guess this is a little bit misleading since we actually have the row of zeros here. So like if you want to query this point, instead of just like if this is like y2 x2 instead of y2 x2, we'd have to add 1 since there's like a row of padding. So it'd be y2 plus 1 x2 plus 1. Yeah. Anything else about this code?
Why do you have the first line of prefix, like, it's inside the 4i and read them, and you have like the fourth line of that is, why do you have that?
Oh, this is to construct our prefix array. Since like it's not something we're given, we have to like construct that based off the grade we get. So this just is our construction formula from here. I don't know if I understood your question.
Yeah, I just didn't understand you, sorry, that's my bad. I got it.
Oh, okay. Yeah, so this constructs our prefix array. Any other questions?
Oh, that's the.
Yeah.
Why do we use a strip instead of split?
Oh, here, so I think technically we could also omit strip. It just will add an extra new line to the end of our grid. But here we don't split because they're not separated by any spaces. So we just like want the raw string and then we want to convert it into a list. So that's what like input.strip just gets like a line and then removes any trailing white space from the end. And then list converts that string into like a list of its individual characters. So that's how we get the input. Okay, any other questions? All right. This again, this code will be available on the slides after we post it. And here's your attendance form. Fill it out, give us feedback. Any feedback is helpful. We also noticed yesterday to sum of 2 values, there were over 100 impact submissions. Feel free to come to problem solving session today and like ask for help, work together on it. You can come to problems in general, you can come to any problem solving session for help on any problem, either that day's or a past problem. So yeah. Thank you for coming today. We'll now start problem solving session and we'll have pizza in about an hour.